Okay, we see the presentation, and that the title of the talk is the multiplicities of non-acyclic SL2 representations and L functions of twisted Whitehead links. Please.
Thank you for introduction. I'm happy to join this conference again. I think this is the fourth time I join this conference. I'm going to talk about the multiplicity of non-acyclic SL2 representation and L functions of twisted Whitehead links. This is a joint work with Leo Bernard, Liu Tange, and Tran. Here is the plan of my talk. Firstly, I'd like to explain my motivation and previous research on twist knots. And then we will explain the Whitehead link case. Afterwards, I will explain its generalization to the general odd twisted Whitehead links. And finally, I will give a remark on the so-called the algebraic L function. Okay, let's start the introduction. My studies belong to arithmetic topology. It's something between number theory and low-dimensional topology, as Tateno-san explained. And in number theory, we have Iwasawa theory and Hida-Maser theory. They are GL1 representation theory or GL2 or SL2 representation theory. In low-dimensional topology, we have Alexander Fox theory, and we are interested in what should be there. And there are a sequence of several previous researches due to I and Professor Morishita and others. I will explain this part. This study is already on the archive, so you can check it. Okay. Let me explain something about non-acyclic representation. Let pi be any discrete group, F a finite field, or a CDVR with LHGL field being F, and rho bar be a representation of the finite field F. Then we may define so-called the inverse deformation of rho over O. This is a lift of rho bar to an algebra over O algebra with some universality. And if we consider the twisted homology, sometimes it is a torsion module, and its order is called the algebraic L function of the universal deformation rho bar, Bolt rho. And Barry-Mazur's question in this situation is that to investigate the multiplicities of zeros of L rho, it is very sensitive and subtle stuff, and it is related to so-called BSD conjecture in number theory, but I don't explain much about this. And please just remember that this is very of interest. And if L is, there are some remarks on L. If L rho is non-trivial, then rho bar is non-acyclic. Here is a definition of non-acyclic. If rho is a representation of an integral domain R, then it is said to be non-acyclic if and only if its a twisted homology over the field is trivial for any I. We have the notion of character variety. SL2, the conjugacy classes of SL2 representations forms an algebraic variety, and it is parameterized by some variants. And we also have the notion of a cyclic torsion function. It is a function defined on the character variety, and it corresponds to and non-acyclic representations correspond to zeros of tau on the character variety f. And there is a one-to-one correspondence. And furthermore, often we have that f and t as polynomials in the same x, y, etc. And the zeros of tau on f equals 0 can be regarded as the intersection of two algebraic varieties f equals 0 and tau equals 0. This is the story. Next, I'd like to recall about the twist knot. Twist knot is defined by the following diagram for each integer n. For example, J22 is the trefoil and J2 minus 2 is the figure 8 knot. And its group is given by the following presentation. And let X be trace A, that is the map from representations to trace row A, and Y be trace AB, that maps row to trace row AB. Then F and tau are both regarded as polynomials in X and Y. And here is our previous result. The intersection of f equals 0 and tau equals 0 is contained in R2 and contained in the straight line x equals y. And at each common 0, these two curves have a common tangent line. If rho is reducible representation, then it is non-cyclic if and only if the representation factors through the -3 surgeries, -3 DN surgery. And as a corollary of this fact, we have that the L function is given by the square of some polynomial. These results were initially observed by several examples. These blue curves and orange curves are of interest, and we can easily see that at each intersection point, they have common tangent line, and these points are all placed on this straight line. We still don't know why this happens, but this is our motivation. We are trying to find more explanation about this phenomenon. And here is our idea. Every twist knots are obtained from the same link, so-called the Whitehead link, by some surgery. So if we study the Whitehead link, then we can obtain the results for every twist knot at the same time. So this is what we will see in section 1. And after that, we can see that the double twist knots are obtained from a twisted Whitehead link. And every twisted Whitehead link is obtained from some surgery from the Borromean link. And our talk explained until this part, and this is for future research. Okay, the Whitehead link is defined by this picture, and its group is given by this presentation. And trace M, trace mu, trace M mu gives coordinate of the character variety. And here is the defining, and this equation defines the character variety. And this part corresponds to the irreducible representations. Indeed, we have the one-to-one correspondence between the irreducible representation modulo conjugate and f equals 0 minus this part. And on the other hand, we have a calculation of the acyclic torsion function. And this is given. It is given in this by this equation. Very simple. And the non-acyclic SL2 representation corresponds to the intersection of f equals 0 minus this part and tau equals 0. So and here is our result, new result. And f equals 0 and tau equals 0 is equivalent to these equations, very simple equations. So furthermore, let us consider the ideal quotient of the polynomial ring by the ideal generated by f and tau. And then under generic localization, we have that this is isomorphic to the quotient by this ideal. Here, there are two polynomials, and here is square. This explains that the common tangent line phenomenon. We can say more. In this situation, f equals 0 and tau equals 0 both define some surfaces, and they intersect. So we have two surfaces intersecting, and at each intersection point, they have common tangent plane. This is very surprising situation. Furthermore, we have that rho is non-cyclic if and only if this rho factors through certain triangle group 3-3 infinity group. This explains the -3 surgery theorem. Next, I will explain its generalization to twisted Whitehead ring. It is defined by this picture. We consider odd twisted Whitehead ring. We need the notion of Chebyshev polynomial. The second kind and the first kind of the Chebyshev polynomials are defined by these equations. In addition, we put V to be this polynomial. Then the geometric component of the character variety of W to n-1 is given by the following polynomial in x, y, z, and v. We can verify that if n equals 0 is a smooth variety. We also have calculation of a cyclic torsion function. It is also given by x, y, z, and v. And this function pk in v. So this is a rational function in x, y, z, and v. But we can verify that the quotient of this point. I think this is also polynomial. So we have the quotient of the polynomial ring in XYZ by the ideal generated by Fn and tau n is isomorphic to the quotient of polynomial ring in XYZ by by ideal generated by these three polynomials. By using Euclidean algorithm under a generic localization, we obtain that this ideal can be replaced by this ideal generated by this and this and this. And we can see that here is the square. So under generic localization, we have that this ring is homomorphic to this ring. Here we have some polynomial g and h. And g and h are generically transverse. Indeed, the main point of our argument was to define the notion of multiplicity, and in this situation. And we believe that this definition is quite natural in this situation and compatible with long history of algebraic geometry. And from this isomorphism, we deduce that that for W2n minus 1, we also have the phenomenon of multiplicity 2. Finally, I'll give some remark on L and stop. Let F be a finite field and O be a CDVR as in section 0. And let pi be the link group of W2n minus 1. Then here is our theorem. Let rho bar be an absolutely irreducible representation of a finite field at A bar, B bar, C bar on Fn equals 0 in F3. And suppose that, suppose this. And let AB be an element of O2, which is a lift of A bar, B bar. Then the Hensel's lemma is that we have that is the implicit function of Fn equals 0 at around A and B. In this situation, we can prove that we have a universal deformation of rho bar over O. This is proved by the existence of Riley's universal representation, and we also use Nissi and Carayol's theorem. And we can, in addition, verify that this module is torsion, and L Bordeaux is defined. And we can say that L rho is equal to the image of tau via the Hensel's map. And by our theorem, by this isomorphism, we can say that the multiplicities of zeros of L rho are at least 2. This is the goal of my talk. There are some further problems. In the twist knot case, we have some numerical studies, and we should do the similar thing for this case, but it's a bit difficult because they have multiple variants. And -3 surgery theorem for general twist knot, twisted Whitehead ring is not yet to be proved. And anyway, we are still looking for more reason for multiplicity too. It's still in mystery. That's all. Thank you for listening.
Thank you for a nice talk.